Okay. Good morning. My name's Dr. Peggy Norris, and I'm with the Sanford Underground Research Facilities Education and Outreach team. This morning I want to talk to you about the gold that was found in the Homestake mine. We heard a video earlier today about the geology of the Black Hills and how the gold was formed in the Black Hills. I want to step back about another 4.5 billion years to when the gold was forged in the solar system to begin with, and looking at the origin of the gold in the stars. So this is a topic called nucleosynthesis, which is the synthesis of nuclei. This talk is basically a high school level talk with some activities that you can do as we go along or offline later, and we'll be happy to answer any questions at the end. So I want to start with something everybody should be familiar with, and that's the periodic table of the elements. And I have gold circled here. So gold is considered a precious metal. So what does that mean? That means that it's relatively rare on Earth. If there was as much gold on Earth as there was oxygen, it wouldn't be going for $1,500 an ounce for sure. So why is that? Why do we have so much less gold than we have other elements? And besides just its use in jewelry, gold is really important in other things too, including the cell phones that you use every day. One iPhone uses 46 different elements. And some of these elements are common, some of them are more rare. Some of them are actually in danger of running out in the next decades. So this version of the periodic table from the European Chemical Society looks very different. Each box is proportional to how much of that element exists on Earth. And so you see the biggest box is oxygen, and that is the most abundant element on Earth. And many of the precious metals and rare earths are relatively small boxes. You also can see which of those elements came from the cell phones, are used in the cell phones. And the boxes in red are in serious threat of running out in the next 100 years. So your children and your grandchildren may be having trouble getting the cell phones that they need because of the elements being missing. The orange boxes are a rising threat because the use of them has gone up so much, and so forth. So it's important to think in the future about how we are going to deal with this, whether it's mining elements from asteroids or some other means of getting these elements that we need, or learning how to design technology that does not use them. So we're going to talk in more detail about the origin of these elements and why some of them are so much lower abundance than others. So I'd like to start with the life cycle of a star, because the elements are forged in stars at various points in their life. And stars are made from nebula, which are areas of dense gases. The gases will start to attract by gravity, and as they attract, they'll start rotating. So you can see in this little animation, this is called they become what happened? Excuse me. That was supposed to stay in Prezi. So, 1 second. Okay. All right. So, don't know what happened that did not happen before. I'll just move on. That makes a protostar and then eventually collapses into a dense enough area where it can start burning fuel and making glowing and making a star. So the sun is an average sized star, and here's just a picture of it with an interesting solar flare. And during the sun, I don't know why it's popping into YouTube all of a sudden. So, but okay. So we'll skip the video. Having a little bit of technology issues, so I'm sorry. But we're going to look at what's going on in the center of the sun. And my assistants, Caitlyn and Adrian, are going to demonstrate the nuclear fusion that's happening in the center of the sun with some magnetic marbles. So the sun is primarily hydrogen, and it's a hydrogen burning star. That means that the hydrogen is going to fuse into helium. So we start with protons. That's a hydrogen nucleus. And as the density gets bigger, you can overcome that what's called the Coulomb barrier from the positive charges of those protons. And they can briefly stick together into what's called a diproton. But very quickly it will beta decay, and one of those protons is going to turn into a neutron. And when that happens, it gives off energy. It also gives off a positron, which is a positively charged electron, and a neutrino. So during beta decay, we get neutrinos, and the sun is doing a lot of beta decays. The next step is that deuteron, which is the heavy proton, fuses with another proton. You get more energy out, and you make helium-3. That's more stable than a deuteron, so energy is released. And then, once you have enough helium-3s around, two of them will find each other. They will fuse and make the most stable element of all, helium-4. So we end up with 4 protons fusing together to make one helium-4. And we can't really look into the core of the sun to see that that's really happening, but based on the light and the energy that's released, it's our understanding. And then in the 1960s, the Ray Davis experiment at Homestake confirmed that by measuring these neutrinos, it confirmed that we really do understand the nuclear reactions that are happening in the sun. So that is the first step. Now, our sun is a pretty small star, and it's not going to go beyond fusing hydrogen. When it runs out of hydrogen, it's actually going to stop its stellar fusion stage and move on to a red giant phase. So right now, we believe our solar system is 4.5 billion years old. So the sun's been burning for 4.5 billion years. It's got about another 4.5 billion years to go before it runs out of hydrogen, so we don't have to worry about it right now. But when that happens, it's going to blow up to basically the size of Jupiter's orbit. So at that point, the Earth's a goner, and it will be burned up along with everything between here and between the sun and Jupiter. After it does that, it will collapse into a bunch of gas called a planetary nebula, and eventually a white dwarf. So that's the fate of our sun. That whole thing should take about 14 billion years. So we got a ways to go before that happens. But if we have a heavier star, they've found stars about 60 to 100 times more massive than the sun. And in those stars, you can actually have multiple stages of fusion. So after the hydrogen is burned up and the star starts collapsing, then it has enough mass that it can start burning helium. And you'll get 2 heliums, 3 heliums to fuse to make an oxygen. And then you'll start making all the elements up to iron. And it ends there. And the reason for that is, I'm going to come back to that in a second, is that up to iron, fusion will release energy, which will help the star burn. But beyond iron, fusion's going, you can see this curve is starting to go down. Fusion's going to take energy to happen. And so in stellar fusion, we only have fusion up to an iron core. I'm going to just back up for a second and point out that there's this really cool website that you might want to go to and play with later that's a little game of trying to do stellar fusion to make iron. It's a very simple, low-tech game, and it's fun to play. Okay, so now we need to figure out what's happening beyond iron. How do we make the things heavier than that? And that starts to come along in the next phases of a star's life when it begins to die. And this is a common diagram that's used in astronomy. When astronomers first started looking and cataloging the stars, they discovered that they could find these patterns. This is surface temperature going up this direction toward the origin, and then the brightness on the y-axis. And the stars that are undergoing stellar fusion all lie on this main sequence. So they're along here. The low mass stars are down toward the bottom, and the high mass stars are up toward the top. As they run out of fuel and they start expanding into the red giant phase, that's up in here. So lower temperature, but brighter. And if they're massive enough, they can make a supergiant, but the low mass and average stars make red giants. So we think that many elements are made during these red giant and supergiant phases. And the Caspar experiment here at Sanford Lab is measuring reactions that they believe are happening in various times in these stages for certain stars, and trying to get input into the models that are being used. So it's thought that that stars close to 1 solar mass go through a stage called asymptotic giant branch. So they've gone through, they've started into the red giant, and then they've collapsed and done a little more burning, and then they kind of go off on this other track. And they believe that in that area, then there's reactions happening that create neutrons. And that's really important for the formation of elements, because it's believed that with those neutrons, you can have a process called the S process. The S process stands for slow neutron capture. And this is not Caspar data. This is data from older experiments and theory. You can see how complicated the reaction rates are for some of these reactions that they're trying to measure. And they are repeating some of these measurements in Caspar. For example, alpha 22 neon alpha releasing a neutron and making 25 magnesium. That's an important nuclear reaction to know and for the modeling of the S process. So we're going to look at that a little more closely, and we're going to model it very simply on our own. In the S process, a neutron could be captured every 10 years or so if the nucleus is stable or has not yet undergone beta decay. So I'm going to show you how that works. And we put a couple of links on to the website that you can download a PDF and instructions for doing this yourself. This is the PDF we put up, goes all the way from iron to gold, so you can track the whole way if you would like. But I'm just showing you the very lowest corner of the front of that PDF. And if you try to print it, it's an 11 by 17 inch sheet, so you might have to print it in pieces. But you can draw, there's instructions for just using the PDF online and drawing arrows. So this is something called the chart of the nuclides. It's used by nuclear physicists because when we do nuclear reactions, we have to be concerned with the total number of neutrons as well as protons. So we need to look at individual isotopes. So an isotope of an element is the proton number determines what the element is, and then the neutron number determines what the isotope is. So for example, down here for iron, along the x-axis, we have the neutron number. Along the y-axis, we have the proton number. So each row is a different element. And for iron, since we ended stellar fusion with iron, there's actually 3 stable isotopes, iron 56, 57, and 58. All right. So if you're in an S process area, then those can each, they'll be around forever basically, so they can run into a neutron and capture it. So the iron 56 will move to iron 57 when it captures a neutron. It'll move to iron 58, and then it'll move to iron 59. Now this whole thing is like once every 10 years on average, so it's taking 10, 20, 30 years to get here, but it's got plenty of time. And when it gets here, iron 59 is not stable. So the lifetime for beta decay is only 44 days. So it's not going to be around for 10 years to find another neutron. So it's going to actually beta decay and make cobalt 59. So that's the next stable element up. So now we've actually made a new element. And then cobalt 59 being stable can capture a neutron to cobalt 60. That's got a 5-year half-life, so it's going to also beta decay. So you can follow this up. And I'm going to let you do this at home, but what you're going to find is that you can make most of the stable, the middle part of the stable elements through this S process. But you're going to be missing some isotopes that have more neutrons or too few neutrons. So like nickel 58 is missed because the cobalt 59 captures a neutron and then goes to nickel 60, and that captures a neutron. So you can't use the S process to get to nickel 58. So that's happening someplace else in the cosmos. So the scientists use these models, and the input, the nuclear reaction rates and lifetimes is really, really important to input into these models to understand how the elements were made. So I'm going to leave that to you to do an exercise at home of drawing out the S process through some of these elements and getting an idea of what you can make that way. But it doesn't explain everything. And scientists as early as the 1950s realized that there had to be another process happening somewhere in the cosmos that they called the R process. And you notice that when you look at the abundances, there's a lot of structure. And that structure is caused by the fact that nuclei have shells, and they have, just like electrons have shells, you might have studied in chemistry class, and closed shells are more stable than shells that have not enough neutrons or protons to fill them. And so that determines a lot about what's going on in the cosmos as well, in the elements. But as I said, as early as the 1950s, they realized that there had to be another process happening. And that had to be a process that would happen in a site that had more neutrons. So we're going to move on from the red giant phase into the end of a star's life and look at supernova. So supernova only happen with more massive stars than the sun. The sun will not go through this phase. But when they do happen, it was thought to be a site where over a very short period of time you would get a large explosion that could have a lot of neutrons and perhaps make the elements that we can't make in the S process. And the interesting thing about this is that it ties back to our neutrino physics that's happening here. So this is supernova 1987A, which was the most recent one that happened close to Earth. And it wasn't in our own galaxy, it was in the nearby galaxy, the Large Magellanic Cloud. We're actually way overdue to have a supernova in our galaxy. On average, there's been one in the Milky Way every 300 years, and it's been at least 600 years. So we're expecting one. But for 1987A, you can see a picture on the right before the supernova explosion and on the left after it. So it was very clear in this telescope. If we had one in our own galaxy, it might even be visible during the daytime. So in the past, they have been. They've been studying supernova 1987A ever since it went off. But one really interesting thing about it is that after they saw it, they went back and they looked at neutrino data from some of the earlier neutrino experiments that were running at the time. And they saw an excess of neutrinos. So the neutrinos actually get to the Earth faster than light. So if they had been looking, they might have seen a signal of this supernova before the light signal came in. And so at this point, many neutrino experiments have what they call a cosmic trigger that's searching for neutrinos from supernova exploding in our galaxy or near our galaxy. And DUNE is going to also do this. So one of its goals is to be a kind of a sentinel for an early signal from supernova so that then the telescopes can hone in on that part of space and get the data from it and watch it as it's happening. So that will happen in the future. Now, before 2017, this was the standard periodic table of the origin of the elements, and it was thought that all the heavy stuff that you couldn't explain by the S process is happening in supernova. But they really had some issues with the modeling of getting enough neutrons to explain things like gold and uranium and the very heavy elements. So there was a theory that perhaps some of that was being made in colliding neutron stars. So here's just a diagram of the R process happening. So now you have many more neutrons. Instead of capturing a neutron every 10 years, you might be capturing a neutron every 100 milliseconds or something, so several times a second. So you make a lot more elements that way. And then after the supernova is finished, then they'll beta decay back to stability. So here is an animation of an R process happening. And here you're making things much more neutron rich than you made in the S process, which went up the line of stability. And then afterwards, they beta decay back to stability and make all the very heavy things like uranium and gold. So that's what scientists expect, but the mystery was where that was happening in the cosmos. And they just one aside, that there is a new accelerator going to start very soon at Michigan State University called Frib that will be trying to understand the R process in detail by measuring many of the lifetimes and reaction rates of some of these very neutron-rich elements that aren't naturally found on Earth. So the R process, we think it might have happened in supernova, or it might have happened in neutron stars. So I want to explain just briefly what a neutron star is. So this comes at the very end of a massive star after the supernova. If it's very massive, it'll become a black hole. But if it's less massive, it'll end up as a neutron star. And a neutron star is very, very dense. 1 teaspoon of material weighs 1 billion tons. So that's as much as 10,000 aircraft carriers or 1,000 pyramids in a teaspoon of material. So extremely dense. And in 2017, there was a big event which changed this whole story, because the Laser Interferometer Gravitational Wave Observatory, which is at 2 sites in the US, and Virgo, which is the Italian one, they saw evidence of 2 neutron stars colliding. So they look for gravity waves, and this is just an animation of what, go ahead. Thank you. And this is an animation of 2 neutron stars, or it could be 2 black holes colliding. They start rotating around each other. They're usually in a binary star system, and as they merge, the mass will make a wave of gravity. Okay, so thank you. Okay. So in August 17th of 2017, they saw a signal at Virgo, and they call that a chirp. There's a picture of it. And it actually, they realized pretty quickly that it was low enough mass event that it could be neutron stars. And so they were able to pinpoint a direction that it was coming from, and they told the telescopes around the world. And as soon as it got dark, this telescope, which I think is down in Chile, saw this spot that wasn't in earlier pictures of that part of space. And this is the spot where these 2 neutron stars collided. And so for months afterwards, they studied the electromagnetic signals coming from that with a range of telescopes. And what they saw was that you were getting what they called a kilonova. It's not really a supernova because it's not big enough, so they call it a kilonova. And it was 2 jets of material. Some of them had enough had signals of light, R process nuclei, so it was probably a region of less neutrons, and then a region of lots of neutrons that made the heavier ones. So the bottom line of this was that they saw these elements being made in one jet, and they saw these elements being made in the other jet. And that they estimate that there's enough neutron stars in the cosmos that could account for all the gold and uranium and other heavy elements that we see in the universe. So now we have a different periodic table where instead of supernova, we have merging neutron stars as being the primary source of the gold and the heavier elements in the universe. So I'm just going to end with giving you a task that you can use the same chart of the nuclides that you hopefully downloaded and draw the R process. And now, because it's only going to see a neutron every 100 milliseconds, if you start with iron, you're going to go way, way, way out to very heavy iron isotopes before beta decay happens. And so you'll see a totally different path. You could try different timings to model whether you're making light R process or heavier R process nuclei. And then after the merger or event is over, everything's going to beta decay to stability. So you can find that you can make the very heavy elements this way. So I'm going to end there, and I hope that you try this. I think it's a really interesting activity, and it's current science that scientists are still puzzling over these events.
You have a question.
Perfect.
The question is, how much lead time between a neutrino detection and visual light from the supernova? You might want to rephrase that for you.
Yes. So the question was how much of a lead time between the neutrino signal from a supernova and the visual light. And of course, that's going to depend a lot on how far away the supernova happens. But what happens is that light that's made in a star takes a long time to filter out of the star. So the density of a star, or even a collapsing star in a supernova, is so much that light can take tens or thousands of years to get out of that, whereas a neutrino will get out right away because a neutrino goes through matter. It's not subject to the electromagnetic interaction, so it doesn't get kind of stuck inside. So it could precede it by days, I think, or hours or days, but it's going to really depend on distance. Okay. All right. Well, I will thank you guys, and if you have other questions, send them in and we can answer them. And I hope that you'll try the nucleosynthesis activity and see for yourself how the elements were made. Thank you.